I'm the Future Systems Project Director at the Argonne Leadership Computing Facility. The ALCF, as it's known, is located at Argonne National Lab, which is just south of Chicago in Illinois, United States. Our center is one of two centers that forms the DOE, Department of Energy, Leadership Computing Facility. And our mission is to accelerate major scientific discoveries and technical engineering breakthroughs on those systems by providing world-class leadership scale computers and resources for the users. Our systems are two of the world's largest in the world. We have a GPU-based system at Oak Ridge called Titan, and our IBM Blue Gene Q mini-core homogeneous system called Mira at Argonne. One of the things that is unique about the Leadership Computing Facility at the DOE is that we must have two diverse architectures, and that's why we have those two sites. Mira, our current production computer, is a 10 petaflop IBM Blue Gene Q. It has around just under 50,000 compute nodes, and each of those nodes has 16 processors with 4 hardware threads each, so we have a lot of hardware threads. It's a massively parallel system. But not only do you need big compute power, you also need a lot of memory, and we provide a high-speed, low-latency interconnect. We have a big data storage system, and this is all in order to support the science on our systems. I'll give you an example of one of the kinds of science that you see on our system. This is a project currently ongoing to explore safer transport mechanisms for explosions. Back in 2005, a big semi-truck was transporting 35,000 tons of explosives. It crashed and caught on fire while it was going through a canyon in Utah. Luckily, there was about 3 minutes between when it caught on fire and when it detonated, and created a huge hole in the highway. It was about that 3 minutes allowed the driver and the motorist who were around to escape, so they didn't, there was no fatalities. But the odd thing is that the explosive cylinders that were actually transporting this material, they should not have detonated. They were explicitly designed to use a combustion method called deflagration that is supposed to burn pretty slowly. So it shouldn't have gone past the speed of sound. And combustion, a detonation, occurs when it goes supersonic and it triggers a high pressure shock wave. For some reason it did. So the University of Utah scientists are doing research, doing these 3D simulations on Mira to try and understand the physical mechanisms that caused that explosion to occur so that they could correct the design flaw in those cylinders so that this won't happen again in the future. Because you can imagine, luckily it was sort of out in the middle of nowhere. Could have been much worse. So that's an example of the kind of science we do on our systems. Let me talk a little bit about the future. The future is Aurora. This is our new system. And it came about as the result of something called Coral, which many of you will have heard about. Coral is the collaboration of Oak Ridge, Argonne, and Lawrence Livermore National Laboratories. It was formed around 2011-2012 in order to acquire the next generation of the leadership capability systems for DOE. So that would be one system sited at each of the sites, one at Argonne, Livermore, and Oak Ridge. We had that requirement again that there had to be architectural diversity between the two systems at Argonne and Oak Ridge. And that RFP was released in January of 2014. The proposals were evaluated, and the winning set, and this is really important, the winning set of proposals was selected in March. Those contracts have all been negotiated and the systems have been announced. So you may be familiar with what was selected, but I will explain again that it was 2 winning proposals, so it was a winning set, and together those two formed the best solution for DOE's leadership class computing. Argonne selected the Intel Prime Cray integrator system, and I'll explain why in just a minute, and Oak Ridge and Livermore went with the IBM GPU-based system. So we have actually got 2 systems out of the deal. We have a new system called Theta, and that's named after the Theta Aurora, and another one coming later called Aurora, which is named after the Aurora Borealis. And they are Intel Xeon Phi compute architecture. So again, many core homogeneous systems. They also have a very innovative deep memory hierarchy with some super fast memory and some slightly slower capacity memory, so a fair bit. The Aurora system will also have the Intel OmniPath network. And the reason why we chose these systems is because they are the right path for our users. Our users are used to the many core homogeneous systems, and so that allowed them to really be an evolution, not a revolution for them. So that combined along with the x86 compatibility of the processor meant that our users should be able to port their codes to these systems pretty trivially. It shouldn't be too much effort to get running. Then they may have to put in some additional effort to get the optimizations and take advantage of the features, but they should be able to do it. Also, our current system is a very well-balanced system. That's one of our goals. And these systems are also well-balanced between the compute, the memory bandwidth, the network speeds, and the storage that we have. For our users, there is one big change. They'll be going from the IBM software stack to the Cray software stack. However, the Cray software stack is pretty robust and it's very well known. And for Aurora, it will come with some exciting Intel innovations. I'll talk a little bit about the systems. Theta is coming next summer. Its primary role is to be a stepping stone for Aurora, to allow our users to get onto the system and transfer then later to Aurora. It is going to be a reasonable size system, over 8.5 peak petaflops. It will also then transition to a data analytics system, so it's got a lot of features that work well for that. I mentioned it's got the Intel Xeon Phi. It's a second generation KNL based. We have configured the nodes with 192 gigabytes of memory, which is really important. That's sort of our slow capacity memory. And then there'll be up to 16 gigabytes of the high bandwidth memory. We've also put 128 gigabyte SSDs on each node so that users can start exploring that space, which we think is going to be important for EXASCALE. It has the Cray Aries high-speed interconnect. It's in a dragonfly topology, which is probably familiar to most users of, say, the NERSC Cray systems. We'll have a Lustre file system on this, and then, of course, that Cray software stack that I mentioned. For Aurora, Aurora is really a major step towards EXASCALE. It's considered a pre-EXASCALE system. And it is more involved in terms of the three-way partnership with Intel and Cray and Argonne working together on the design and development of the system. It will be at least 180 petaflops. It can go up to a lot more. We have options in the contract if we have the money. But more importantly, I think to the scientist is that there's a projected 13 times improvement in application performance for our users. So that's pretty significant. It's also very energy efficient, a lot like our Blue Gene systems, and we will be receiving this in 2018. So Mark is going to tell you next, he was going to go before me, but now I'll come after, all about the Intel HPC Scalable System Framework that is the basis of the design for the system. This system will have the KNH, Intel Xeon Phi. It will have about the same number of nodes as our current system, so as far as system level parallelism goes, it's going to be very similar. Of course, at the node level, it's going to be a little bit more parallelism there. Now, we will have a lot more memory. There'll be more than 7 petabytes of total system memory. That's a combined between the super fast memory that I mentioned and the slower capacity memory. And it will have the new Intel OmniPath architecture. Some of you guys may know it. I'm going to mention this as Storm Lake 2. It'll be the second generation, built using silicon photonics technology, and it'll also be in the dragonfly topology. And I mention that because as you look at this, you can see from Mira to Theta to Aurora is a great path, in that there's a lot of evolution in there, getting better, more powerful improvements, but there's also some revolution in there as well, but nothing that's going to scare the users, which is important for us. And we'll also have a very large Lustre file system at a reasonable performance. One of the mandates we have at the Leadership Computing Facility is that we are supposed to have science, real science, big science, solving real science problems happening on day one. So immediately after acceptance, we need the scientists to be on running at scale. And our mechanism for doing that is called the Early Science Program. Our early science program that we're doing for these systems is based on something we pioneered for Mira. We had 16 projects running at scale on the machine day one, and that's our goal here. This early science program is really a partnership between the users, the vendors, and ourselves. The users, the science code teams, they provide the science domain expertise, development time, and also a commitment to the community to provide back knowledge about what they've done to optimize for the system, and that's really important. So they commit to that. We at the ALCF provide performance engineers, I/O specialists, computational scientists, time on our current machine to get started, putting in the threading and so forth that you need. A large amount of 3 months of dedicated early science time on the system where they can run just them. They're running their science, as well as some additional time after that. We do workshops for them and provide all kinds of help. And then Intel and Cray step up to the bar as well. They provide deep dives, one-on-one, hands-on experience with them, access to early hardware, early software, all of the expertise they have in the internals. So it's a really great deal. Now I'll mention that the Theta ESP is already underway. The call for proposals closed a few weeks ago. We're currently in the process of selecting the final set. But if you want to get in on it, next year in Q3, we'll be having the call for the Aurora ESP. So we'll be looking for science. It's US and international. Our machines are open science systems that are available to anybody in the world who meets the requirements. Just a little bit, and then I'll let Mark take over, about some of the science that you might see that's enabled by Aurora. Here are 3 areas. One, material science, that's primarily batteries. One is another that we think is going to be on there is climate science, and then some in renewable energy. On the battery front, they're trying to discover specific materials that will improve batteries. So, you know, the kind of standard stuff you would think. You want better density, you want safer, you want longer life, you want them to be stable. So that's the kind of research they're doing. That's ongoing right now, and they'll be able to do more with Aurora. In the climate science, they're looking at better resolution. They're looking at pulling in more processes, such as the carbon cycle processes. They're looking at bringing in observational data, et cetera. So that's something that they're going to need the more powerful computing and data resources that we have. On the renewable energy side, there's a couple of main thrusts there. One is wind turbines. The turbine blades can be modeled, just a piece of the blade are modeled on Mira today. And what they're looking to do is try and model the whole blade as well as the whole turbine, and ultimately to model farms of them so they can understand what's the impact of the flow for the wind over turbines near another turbine, so that kind of thing. And there's also a lot on our systems looking at the power grid. How do you take renewable energies that have varying time, you know, amounts of power that's provided based on time, as well as based on geography and the location. These are all things that will be enabled by the more powerful supercomputer that's coming. So in summary, I would say that for us, we believe the future looks really bright. And we think it's because we have these 2 very highly scalable, very balanced computers that are coming for the world's open science community. They will have a robust and full-featured user environment, so our user will be happy. It's a homogeneous mini-core node architecture, which is an evolution. And we believe these apps will be able to transition to the new systems with relatively minor